All right, hi everyone. Let's start doing a review on chapter 21 and 22 for our exam 2. So the first topic will be simple regression model. Most of these topics are what we have explained multiple times. We go over these multiple times. And also when I explain the multiple regression, many of those topics are still the same. So you remember for simple regression model, we're trying to estimate a response variable or DV using changes in explanatory variable or IVX. So the first step we always start with is estimating in estimation of your response variable is creating a scatter plot. So scatter plot shows if the relation exists, and more importantly, what we're looking into when we look at a scatter plot is we want to see if the relation is linear or it's not linear. Why are we looking into a linear relation? Because we are going to use a line to estimate the behavior of values of our DV, and as a result, that line creates a more accurate and more reliable solution for us if the relation is also linear. So in this case, you can see that we are estimating the production time based on number of units in order. And this equation is called regression model. Simple regression model is a model for association in the population between an explanatory variable and response Y. Consider the data to be sampled from a population. Other ways of representing a simple regression model, you can see down here, is mu, and mu is a population's average, right? Population average of Y given for values of X, or in other words, we also show it with expected value of Y given for a specific value of X. And normally we represent it in many questions that you have on exam and on your homeworks. You always see beta 0, beta 1. So beta 0 represents intercept, beta 1 represents slope, right? And how we interpret these. So beta 0 is when we have no effect from X. What is the estimation of your response variable? Beta 1, when you want to go for interpreting it, you will say if there is 1 unit change, in explanatory variable IV, the amount of estimation change in response variable will be beta 1. So if beta 1 is positive, there will be increase. If beta 1 is negative, there will be decrease when there is 1 unit increase in independence variable or explanatory variable. So since the left-hand side of this equation, our response is always an estimation. So since this is an estimation, it's not exact number, there's always error involved. So we call these errors residuals, and these residuals should have certain properties. So one of those properties is that in average, the the expected value of these residuals should be 0. One reason is when you look at the scatter plot, that the line goes through the data. If the line goes through the data, there has to be almost equal number of points on top and bottom of the line. And if these distribution of these points around the line are normally distributed, and there are enough similar amount on top and bottom of the line, you will have, the positive one are on top, negative numbers are below. So they cancel each other, and that creates expected value of 0. That's how we show it. In general, there are 3 conditions for residuals or errors of a simple regression model that is required for us to check. And these 3 are important because we want to make sure this regression model is reliable. And once again, if these 3 assumptions or these 3 conditions have met, what happens is these 3 conditions are telling us the regression line is reliable because the scatter plot of those data are looking like a linear relation. There is not high variation among them, so you don't have many points very far on top or bottom. They're normally around a line, and also the errors do not create a pattern. That means you don't have a bunch of these points around one area of the line, and on the other area of the line you have no points. Okay, so what are these conditions exactly? These are the 3 that we have worked a lot on. We have repeated these a lot. So we want residuals to be independent. Errors are independent of each other. Equivalent to this, we can say that we want residuals to have no pattern. If there is a pattern, then they're not independent. They become dependent, right? And do you remember the method we use for this, for independence? Or for dependence of errors? One method was residual plot, where x-axis is IV, y-axis is the residual values. The other one was Durbin-Watson test. Durbin-Watson test was a test. If D is close to 2, we would say residuals are independent. Otherwise, the residuals are not independent. The second condition is equal variances. That means throughout the whole regression line, we have similar variance, similar variation around the line. So what I do is I muted everyone just to make sure by mistake no one is talking. If you want to talk, please feel free to unmute yourself and just come up and talk, okay? Or you can type in the chat area. So we want to see equal variances. And if there is no equal variances, that means, again, this line is not actually representing the relation. Michelle's saying that very much increase the quality. All right, thanks. Always let me know what you hear on your side, okay? All errors have the same variance, and the variance is equal to sigma square of epsilon. And the last condition is we want to see normally distributed data. So how do we know this data is normally distributed? Number of those points close to the line are supposed to be more. That creates that bell shape that we are looking for here. If many of these points are not around the line, that means there is a problem with our regression model. So let's just go back to JUMP and just check a few things right here, very quick. So let's say response variable is says. So we're going to work on a simple regression model. So in the simple regression model, you remember that your response variable is continuous DV. Your explanatory variable or IV is also continuous. So it's relation between two continuous variable. To go ahead and analyze this, we go to analyze, go to fit y by x, because it's a one-on-one regression analysis. So bring in sales, which is your dependent variable, and bring in your number of employees, probably. That would be a good option. So I want to see if there is relation or association between number of employees and sales in a company based on the data that we have. Well, so that's the relation, that's the equation, that's the scatter plot that we have. To get more information, what is very obvious here is we have an outlier here. Later we'll delete it to see what changes we have. So I need to get more information. So I click on rectangle. I can see that this linear relation exists here and two outliers out there. So I click summary statistics. So summary statistics helped me to get correlation value, which is 97% with p-value below 0.05, with a p-value below 0.05. And what else can we get? We can find a fit line. So click on fit line. That would give us the equation of regression model, which is saying estimated values of sale in $1 million is equal to negative 603.69 plus 0.15 times number of employees. All right, so R square is important here. R square represents percentage. So you multiply that number by 100, that becomes 94.7% of variation in response variable sales is explained by variation coming from number of employees IV. All right, so what else are we looking at here? We're also looking at the parameter estimates table. And below that, you can see your intercept. The value is exactly the same as here. And your slope of number of employees is exactly the same as number here. So what we're looking to here is the p-values. The p-values are supposed to be below 0.05 if the model is reliable. But you can see that the intercept is not below 0.05. Something's wrong with this model, right? So we need to check those conditions at this point. So to check those conditions, we need residual values. So to find residual values and save them and explore what's happening there, we can, on the fit line, rectangle of fit line, click. For you to see, I should go here and find residuals, save residuals. So we save residuals. What happens is residuals are being saved at the end of your data set, right there. And so now we have a chance to work on these and get some more information. So go to analyze distribution. So we want to analyze the residuals based on their distribution. So I drag and drop residuals into Y columns, click OK. One of the things I'm looking at here is a histogram. So I want this histogram to be more valuable for me. So I go to histogram options and make sure it looks like the way I need to see it. I can see that it's not normal. Mainly one reason could be because of that far outlier here, And looking at the box plot, I can see that I don't have that much normality here. However, these are not methods we learned for checking normality. One other method you learned was Quantile Plot, right? So that's also in your book. So click on the red triangle, normal quantile plot is right there. So you want to check the quantile plot. That's a quantile plot. So let's see. We have about 32 data, right? And you can see these points are supposed to be around this line. They're not supposed to be on these outer boundaries, upper bound and lower bound. They're not supposed to be around there. They're supposed to be around this line in the center. So you can see how many of them are outside. We want to see 95% of them inside the boundaries, okay? Inside the upper bound and lower bound. So let's see, 1, 2, 3, 4, 5, 6 of them, as I can see, 6 of them are outside. So 6 out of 32, that's more than 5%. So this is telling me this data is not normally distributed. And you also learn another method for checking normality, if you remember. There are 2 other methods. One is Shapiro-Wilk, right? Another one is checking skewness and kurtosis. Skewness, kurtosis, where do we get those? Down here in summary statistics, I click on customize and add what I need, skewness, kurtosis. And then that's it for me. So just click OK. You can see kurtosis is 13, skewness is negative 2.9. The general rule for most problems for social sciences, we normally use skewness, kurtosis between -1 and 1. So if the skewness, kurtosis are between -1 and 1, we assume that we have a normally distributed data. None of these two are between -1 and 1. So this is another way to check normality of residuals. Are these two numbers between -1 and 1? No. Okay. So the other method that we learned earlier was using Shapiro-Wilk test. So go very fast over it. You have another video recorded when I explain this completely. So you go to a triangle, you go down here to continuous fit, and this is too large. Go down here to continuous fit and enable legacy feeders. Enable legacy feeders. So now going back one more time into continuous fit. Let's check if fit normal works. Fit normal. That's fitted normal. And if you go back up, you can see that it fits a normal curve for us here to see some results. And you can see that it's not a good fit to this normal distribution. So let's see if we have more information here to see. Let me check this one more time. if you go down here on residuals one more time, legacy feeders, continuous feed, legacy feeders, continuous feed, you can see normal here. Click on normal. So that is a normal distribution. That's for Shapiro-Wilk test, okay? It's in red color. The green color was not Shapiro-Wilk. So let me do this one more time just to make sure everyone is understanding this clearly. So I go to distribution, residuals, go to Y columns. So we just go over the Shapiro-Wilk one more time. Residuals, continuous feed, legacy, enable legacy feeders. And after that, one more time, go here, legacy feeders, continuous feed, and normal. You do that, that create that normal curve. I want to see that histogram with rotation 90 degrees. So now it's time for me to find Shapiro-Wilk. Shapiro-Wilk should be right here. Goodness of fit. So under fitted normal table, with triangle, goodness of fit, that gives you Shapiro-Wilk. It's right there. So what's the rule for Shapiro-Wilk? How do we determine data or residuals are normal or not here using Shapiro-Wilk? If the p-value is more than 0.05, if the p-value is more than 0.05, residuals are normal. One more time. If p-value is more than 0.05, residuals are normal. So let me write this on a Word file so you can see. So checking normality of data. So in this case for residuals, doesn't matter for residuals or any other data when you want to check normality using Shapiro-Wilk. Shapiro-Wilk test has a p-value, right? If p-value is more than 0.05, then we can say that data is normal. It's opposite of what you have seen in the past, okay? That's how Shapiro-Wilk test works. If p-value is more than 0.05, data is normal. Otherwise, if p-value is less than or equal to, less than or equal to 0.05, then data is not normally distributed. Make sense? Okay, so I give you a second to write this down and then I continue. All right, so I hope that was good enough for you to remember how to check normality. So that was for normality, right? So one way is Shapiro-Wilk, one way is the skewness kurtosis to be between -1 and 1. Write that too. Or use skewness and kurtosis. And we represent skewness using SK, kurtosis using KR, and SK and KR to be between +1 and -1. Okay, this means data is normal and otherwise not normal. Otherwise not normal. And another method is Quantile Plot. That's in your book, so you can check that. Okay, so let's just continue. Is there any question? Are you all good?
We're good. I'm good.
Okay. All right. Perfect. So perfect. So next, I wanted to show you. So that was for normality, right? The next is checking for similar variances or equal variances, and the other one was checking for independence of residuals. So go to analyze and fit y by x. What we're about to do is we want to create a scatter plot where x-axis is our IV, x-axis is our IV, which is number of employees. But DV is not our DV anymore, it's not sales, is our residuals. Residual go to Y, and that's it. Residuals Y, and IV goes to X. So what we hope we can see here is, we hope to see a data set, a set of residuals where they're not having any pattern, first of all. Second, they have similar variances. So to check that, you need to go to fit line, red triangle fit line, that creates the horizontal line for us. That's the horizontal line. Look, the residuals seem to have a pattern. From left to right, they are decreasing. They're decreasing, right? That shows that we don't have, that independence. We don't have that independence of residuals. How about variation? At the beginning, the variation is here, here, small here, large here again, small here. So you can see that even we don't have similar variances, we don't have normality, we don't have independence of residuals. As a result, the model that we found earlier is not a reliable model. That's the model, if I'm not mistaken. That's the model, yes. That model is not reliable. And it's being confirmed using the p-value of the model, because the intercept has a p-value more than 0.05. So let's try to resolve these problems and see if this can be resolved, okay? So one method we can use, one of the things that is affecting here is effect of an outlier. So checking the outlier, if I close this, I know this model is not working for me, so I close this, and what I do is I check for outliers. I remind you, for exam, removing outliers is not required. Whatever the result is from the actual data that the question is giving you. You just make decision based on that, unless the question asks you to remove any specific value, okay? Otherwise, do not remove any outliers. So let me see. So to check outliers, we go to Analyze, Multivariate Methods, Multivariate, Analyze Multivariate Methods, Multivariate. Another thing that I have to add about residuals is that we remove residuals. Normally when we have enough data, we have a big set of data. If you don't have a big set of data, we minimize removing outliers as much as possible. So in this case, we have 32. Maybe we just remove 2 or 3 data, okay? So I want to see relation between sales and number of employees. This is multivariate methods, multivariate. They both, IVDV, they both go to Y columns. Click OK. So these are the scatter plots. That's not what we are looking for here. We're looking for outlier analysis under multivariate red triangle. Down here on the left-hand side, you have outlier analysis. And since you don't see it, I have to move this a little to the right. One more time, outlier analysis. And there are 3 different methods. I uploaded link of a video that explains all 3 different types of outlier analysis. I use Mahal test or Mahal test. It's right there. So according to this test, 2 of these variables are too far and they're having negative effect on our results. How do we know which rows they are? I just put the cursor on it. That's 28. The cursor on it, don't click, just the cursor. That tells you which row it is. Row 32 and row 28. So there are different ways to exclude them from results. I think if you right click here, that gives you, it should give you, or maybe you should click on it first and then right click. Up here you can see row exclude. Or if you don't want to do it this way, you just remember the numbers 28 and 32. So go back here, right click on row 32 and simply hide and exclude it. And also 28. That's 28. Right click, hide and exclude. All right, so I redo the analysis. Fit Y by X, sales, number of employees. Again, we're not 100% sure that only these outliers are the reason that we have those negative effects. And we have a model that's not reliable. We try to check one by one. So I click OK. My scatter plot looks much better this time, right? There is still a problem. There's a big concentration of data down here, but that's not actually a problem. So these are probably more big companies. That's why you have less of them. And all these around here are those smaller companies. So of course, size of company can have some kind of effect here, okay? All right, so what's next? I want to see correlation. Summary statistics. Correlation is 0.93, still high. It's significantly and highly correlated, positive correlation, and then fit line, red triangle fit line. That's my fit line. Now I want to see if this makes sense. So R square is 0.88, 88 point, almost 88.3% of variation in dependent variable sale is explained by number of employees. That's the number. And down here, what I see is actually very satisfying. So you can see that p-value was not significant, was not below 0.05 in earlier analysis we ran before removing. Now after removing, you can see that p-value is below 0.05, and this estimation, this equation now can be a reliable estimation. Other things, do we need to check other things? Yes, we need to check normality of residuals. So I need to take residuals out to do that. Rectangle of linear fit, check save residuals. Rectangle of linear fit, save residuals. So going back here, I can see the residuals are saved here. That's the second one, which you can see 28 and 32 are excluded. They're not in results, right? So let's check this. Analyze. So first I use distribution to check residuals. Normality. And then look, we still don't have that normality. We still have these three outliers are pooling center of data to the right hand side. We're pulling this tail to the right hand side. All right. If we had enough data, we would remove this three as well. Then probably we could have a better results. So let's see how skewness kurtosis look like. So down here, red triangles, customize summary, skewness kurtosis. But skewness got much closer to 1.5. Kurtosis 3. Kurtosis is not. Kurtosis to be more than 1, it's okay. Not too far from 1, but 3 is okay. But skewness 1.5 is still high, and that's because of those 3 outliers we just saw. So let's see if a quantile plot, what the normal quantile plot looks like. Oh, still not good. You can see that the 1, 2, 3, the 3 are on the line or outside. All right, 3 out of 30, is still more than 5%. So they don't indicate normality of residuals. None of these two. And we can check Shepherd-Wilk too. Shepherd-Wilk very fast. Enable legacy and legacy feeder, continuous feed, normal. They have actually changed the way you can find Shepherd-Wilk. So down here we should have fitted normal, the triangle, goodness of fit. P-value is still below 0.05. So this confirms 100% that we don't have normality of residuals here, okay? Let's analyze those last part, the last condition, the last two conditions. So we had number of employees as X, residual 2 as Y. This is much better than the first one. This is much better than the first one. So let's see. fit line. That's what we are about to analyze. So you can say there are approximately, you can see that circle here, almost a circle up here. So we have almost equal amount of points on top and bottom of the line. There is still, I don't call that a pattern, but there's a small pattern here. And in addition to that, do we have similar or equal variances? I would say no, in my opinion. Here, there's a low variation, higher variation, low variation between these three higher, again higher, higher variation, low variation, low variation. So you can see low, high, low, high. So this is not similar, it's going up and down, up and down. It's supposed to be smoothly around the line, up and bottom, okay? So we don't have that condition. We might probably, with some kind of help, we can say they are independent, but actually they're not. So again, those conditions have not met. Okay, we by looking at our outliers, we can see that we still have the chance to remove more outliers, and in addition, we need to know that when you have less data, especially 30 or less than 30 data, that's not good for regression. For regression analysis, you need about 100 to 300 data to have a good regression analysis. All right, so let's go back to slides and move forward. Does anyone has any questions? Are you all doing good? Just you can say yes, no, or just come up and talk. Selena is good. Allison, Olga.
Good.
John. Okay. Nico. Jessica, Sam. Waldo. Good. Okay.
Hello,
So,
hello, Professor.
pardon me?
Professor, can we do an exercise in chapter 21 and go?
No, this is a review session. I don't go over those, and I'm recording this.
Okay.
At the end of the class, I'll stay and answer your question, okay? Okay, and remember that my stat lab reading, you have to read the book first, then do your my stat lab work, okay? If you read the book and understand it, you will never have any problem with the my stat lab. Especially, I opened those help parts, the video parts, and they have instruction, they have solved problems. I expect you to work on those, and because if I want to go over my stat lab problems, that's a lot of work, and I have to go one by one. All right, and again, some of those problems on my stat lab, they have problem. Sometimes they don't have data. They are supposed to provide data. They did not. Sometimes because of rounding, they say round with 2 decimals. They themselves rounded by mistake, less or more. So for that reason, I told you, if you get 80% on each chapter, if you get 80% on each chapter, you will get full credit. Yes, so I know the way that book explains things could be hard for some students to understand, and that's normal. It's not abnormal, okay? I myself, when I first read the book, it was not that clear. I read it again after 2-3 times. Then I saw that it's what actually I know. So it's not something strange. It's just the way it's explained is different, all right? You need to understand that different professors, different scientists, they write and they say things differently. The rounding problem will not be an issue on exam. For exam, what I do, I solve problems myself before I give it to you. So I will make sure that those problems, they don't have any problem. For any reason, if such thing happens, I will know and I will remove that question and give you the credit, give the credit to your other questions. All right. So I'm here to help you and make sure nothing goes wrong. All right. Be sure about that. Like your exam one. Exam one was the same. So we did not have any specific issue on exam one. And all right. So are we good? Okay, so we check normality, we check linearity of relation, and so this is another problem. So you can see that the way we represent our regression model, simple regression model, because residuals are involved now, we add residuals, we add errors to our equation, to our model. We don't have estimation on this side anymore. We have equality, right? And this is how we explain that epsilon or residuals follow normal probability distribution with the average or expected value of 0. It's not the variance of sigma squared. We can see that one more time. We want the observations to be independent of one another, have equal variance around the regression line, and normally distributed around the regression line. Okay, so that's what we just covered. So that's what we expect to see when we have residual plot. So the residual plot should be should look almost like this, like a rectangle, almost equal amount of points on top and bottom of the line, and similar variances from left to right. And we don't see any patterns here, right? We don't see any patterns. From left to right, there's no pattern. So we can say linearity is satisfied, no pattern in residuals, similar variances satisfied, spread of residuals constant around horizontal line. And that's the quantile plot. That's what we expect to see for checking normality. All right, for normality, we expect to see a graph like this. Look, the histogram looks normal. Normal quantile plot, all of these points are between the upper and the lower bound. When it comes to lurking variables, I explained you what lurking variables are. You will not have a question that includes lurking variables problem, okay? But you need to know what lurking variables are, and I believe that we have talked about it. In the past. Then let me see what else we have. Other ways that, different ways in an exam, you will have these signs. Intercept could be shown by beta 0 or B0. Slope, beta 1 or B1. The response variable or dependent variable with the y hat or mu of y given for x. Deviation or residuals by epsilon or by e. The standard deviation of epsilons. Standard deviation of residuals, we call it standard error. Standard error can be shown by SE or sigma of epsilon. So remember these, okay? Because when you go for exam, what happens is when you go for exam, some questions, they use different signs. So you need to know, the question will simply just say, what is beta 0? So they assume that you know what beta 0 means. Beta 0 or B0 is intercept. Beta 1 is a slope. Mu y given for x. That's your response variable, estimated value for y. Epsilon and E residuals. SE and sigma epsilon is for standard error. All right, so we have that formula. So again, the probability of you facing with formulas is very low for exam, maybe 1 in every 30 question, okay? However, I just want to make sure you know what this formula is about. This is your estimated standard error for B1 for the slope. Where do we find this value? Where do we find this value for on jump? Where do we find this value on jump? So let me show you very fast. Let me see if I have it. Yeah, this is the regression result. This is the fit line result, right? You go down to the end, parameter estimates part. Under parameter estimates, you have number of employees, that slope, right? The actual slope value is 0.119. The standard error is this number, that SE, 0.008217. So two times of standard error to the right and left of this estimate value 0.119277722. Two times standard error around it includes approximately 95% of observations. The same thing happens with your intercept. Two times standard error for intercept added and subtracted from 631 should include approximately 95% of your observations. And that's what this is about. So the standard error is influenced by, so this might be, we might have a question on this, okay? Standard error is influenced by standard deviation of residuals. As it increases, the standard error increases. Sample size, it increases, the standard error decreases. Standard deviation of x, as it increases, the standard error increases. And these two graphs, if you remember what they mean, what they represent here, they represent the higher the variation of x values, right? This is not about variation of y values. The higher the variation of x values of independent variable or explanatory variable, the better the estimate of your slope. And why is that? You can see when there's low variation, variation means the difference, right? You can see the difference between x values here is very low, and there are many possible lines representing the same data. But here, because they have high variation on x from left to right, there's a high variation that creates multiple lines that are pretty much close. Even if there is a mistake, there is an error in the system, that won't be give you a very far results. So that would be good. You can see that here says more variation in x leads to better estimate of slope. So take note of this slide. This is important. And inference in regression. So R square, that's what we always reported. Standard error, that's standard deviation of residuals. N is your sample size. B1 and B0, you know what they are now. And p-values are very important. Make sure they're below 0.05. If in the question gave you these numbers and asked you to decide to reject HR or not, if p-value is there, p-value below 0.05, you reject HR. If p-value is not below 0.05, you do not reject HR. If p-value is not given, what do you use? You can use t-statistics if it's available. It has to be more than 2. If t is more than 2, that's equivalent to p-value being less than 0.05. So the 95% confidence interval for your slope and for your intercept, where do we get those on John? Very fast here, I show you that too. So right click on parameter estimates. Right click on parameter estimate, go to column and click on lower 95, column upper 95. These are the numbers. These are the lower and upper. So you don't actually need those formulas. You just need to right click on parameter estimate results and find columns and then click on upper and lower 95%. Okay, so that would be the interval we found. How do we write? How do we write the hypothesis for regression analysis? So this is how we write it. Inference in regression is the hypothesis test. So again, we have beta 1, which is a slope. We have beta 0, which is your intercept. What do we expect? We expect these numbers to be non-zero, right? We expect these numbers to be non-zero, but here they are 0. That's our HO. That's what we want to reject. In what condition do we reject these hypotheses? If p-value is below 0.05 or t is more than 2. So you will have questions that in the middle it says, what is your decision about this hypothesis, HO beta 1 equal to 0? Then you look at p-value, if below 0.05, you say reject HO. Or another question may say, HO beta 1 is 0, is testing what kind of hypothesis? So that's the hypothesis for the slope, right? You want to see that slope is significantly non-zero value. Same goes with the intercept. So remember, beta 0 equal to 0 for HO. That's testing intercept. Beta 1 is testing slope. Okay, so these are just repeats of what I just said again. So that was for chapter 21. Let me check chapter 22 as well. So chapter 22 is actually very much similar to what we covered today. There are a few things added to it. I'm going over those very fast. So changing variation, we said that changing variation is not good. We want similar variances. So in this chapter, what you learned was, so that's what we already covered. P-value more than 0.05 is not good. And we checked this scatter plot and we see that from left to right, there is a pattern, first of all. Second, you can see that variation is low here, medium, low, high. So increasing the square feet, variation is increasing. That is the main reason we have a p-value more than 0.05. And then later, if you remember here, we learned that by checking those conditions are not satisfied, we check using a residual scatter plot, we can see that we don't have similar variances. Another way of checking it is using box plots with groups of data. You can see that they are not similar, they're not equal variances. Another thing we said is if you have equal variances, what do we call it? We call it homoscedastic. So homoscedastic means that we have equal amount of variances of errors, right? If errors do not have equal variances, we call them heteroscedastic. So on your exam, remember, for some questions, they will not say equal variances or not equal variances. They will say homoscedastic and heteroscedastic. So you need to remember, homoscedastic is equal variances, is good. Heteroscedastic is not equal variances, is not good. Heteroscedastic is not good for residuals. Homoscedastic is good for residuals. So that part. So that is the consequence that we have. We can see that more than 5% of those data are outside the range. So when we have that changing variation, there are always solutions. We always have to find out why we have changing variation and try to explore different ways. In this example, we learned that a square foot is the reason we have that large amount of variation. So as a result, we divided both sides by a square foot. So instead of using price to estimate, we use price per square foot to estimate values, and that reduces a lot of variation. So that's what we did last time. We did that in class. And check the results. Variation is controlled. Now you have less variation. Remember, variation always exists, but we don't want too much variation. So box plot confirms homoscedastic errors. And that means they have equal variances. The next step, we look at this graph. This graph shows quantile plot of residuals. Of course, this is showing the data moving more toward normality of residuals. You can see that they're much closer to the actual line, the normal line. It's not perfect, but it's still much better than before. R square is a low value here. And that is not a problem. We have lower R square. We have lower correlation. But what do we get instead? P-values are both less than 0.05. So in the company's data that we checked together, by removing outliers, we could get lower p-values, right? Here, by dividing both sides of the equation by a square foot, we could achieve this. So different problems may require different decisions to make to correct the model. Your job for this course, for this class, is not to correct any models, okay? The only models you might get question on is the ones that you see on examples right here in the book. So something very similar to this. And checking confidence interval of 95% around estimated values. So we learned how to get that confidence level or confidence interval. And then let me check this. Outliers, we just covered it. And I hope you can see that for one outlier, we're supposed to have that regression line, the green line, but because of that outlier, it's shifted to the right-hand side, became the red line. And consequences of outliers. So there will be question on these. I'm sure you have a good understanding of outliers now. Not worried about this part. And for detecting dependence, Durbin-Watson test, we discussed that before. So what's important here is that Durbin-Watson test shows tell us if the residuals are dependent or not. How does it show us if the data is dependent or not? It actually calculates some kind of correlation between residual. So we create lags of residuals, which means we put residuals in one lower and get correlation to itself. We call it autocorrelation. So what is autocorrelation? Correlation of residuals to themselves, adjacent residuals, right? And using that, we create a number, D, for Durbin-Watson. Now, I told you in the past that if D is close to 2, that's telling us residuals are independent. If D is close to 2, if you look at our previous videos, you'll see that Durbin-Watson test for dependence of residuals. So if D is close to 2, then we can say residuals are independent, right? If they're not close to 2, then residuals are not independent. So how is it said in the book? First, hypothesis for Durbin-Watson is written this way. The H null, the negative, in fact, the negative hypothesis is that rho or correlation is 0. Correlation is 0. So do we want correlation to be 0 or do we want to be non-zero? We want correlation of residuals to be 0. So we don't want to reject HO, we want to fail to reject HO, right? Because we want to have independence. We don't want any correlations. So the formula is here. You will never have to use this formula for exams. Just know what the formula looks like. And one way is to use the p-value provided by software table critical values alpha 0.05. But another way to do this is using the value of D. So you can see, depends on how many data you have, depends on the sample size. That's your sample size on the left-hand side. You have different range of values. What are these range of values? If D, coming from software, if D is between these two numbers, residuals are independent. Always, it's easier to remember that if D is close to 2, look, 2 is between these two numbers, these two columns. All of them have lower and upper bound of 2. So if your D or Durbin-Watson value is between these two values, between these two columns, residuals are independent. If it's equal or outside, less than 1 point something and more than 2 point something, residuals are not independent. Next is, so I won't give you any time series question because we will cover that in chapter 27 after exam 2. Okay, so that is pretty much it for tonight, and we made it. It's 8:44, so let me